Hello, beautiful souls. Welcome to this quiet space, a place where minds slow down and hearts rest. Before we begin this gentle, sleepy journey, just a small moment of support. If this meditation brings you calm, comfort, or clarity, please subscribe to the channel, gently tap the like button, and leave a comment to let us know you are here. Your support helps us continue creating these peaceful spaces for your mind, for your heart. Now, there is nothing else you need to do, nothing to think about. Let's begin. Close your eyes now and slowly settle into a comfortable position. Take a gentle breath in and slowly breathe out. Let your shoulders relax, let your jaw loosen, and allow your whole body to feel heavy. We begin by considering what scientists mean when they speak of atmospheric composition, which refers to the collection of gases that surround our planet, held in place by gravity, extending upward from the surface in layers that gradually thin as altitude increases. The atmosphere is not a single uniform substance, but rather a mixture of different molecules, each present in specific proportions that can be measured and described using precise numerical values. When we examine the composition of Earth's atmosphere under normal conditions, we find that approximately 78% consists of nitrogen molecules, each composed of two nitrogen atoms bonded together, and approximately 21% consists of oxygen molecules, also composed of two oxygen atoms bonded together, with the remaining 1% made up of argon, carbon dioxide, water vapor, and trace amounts of other gases. These percentages represent volume fractions, meaning that if we were to imagine a container holding 100 molecules of air, roughly 21 of those molecules would be oxygen, 78 would be nitrogen, and 1 would be other substances. This way of describing composition allows scientists to communicate clearly about the relative abundance of each gas without needing to specify the total quantity of air being discussed. Oxygen concentration, more specifically, refers to the amount of oxygen present in a given volume of air, And this concentration can be expressed in several ways, including as a percentage, as a partial pressure, or as a number of molecules per unit volume. Each of these methods provides a different perspective on the same physical reality, and scientists choose among them depending on which aspect of oxygen behavior they wish to examine or calculate. The oxygen we breathe is distributed throughout the lower atmosphere in a relatively uniform manner due to the constant mixing caused by wind, convection currents, and the random thermal motion of gas molecules, a process that operates continuously without any conscious direction or purpose, simply as a consequence of the physical properties of gases and the energy present in the atmosphere from solar heating and other sources. When we consider what it means for oxygen levels to double, we are imagining a scenario in which the proportion of oxygen molecules in the atmosphere increases from approximately 21% to approximately 42%, while the proportions of other gases adjust accordingly, assuming the total atmospheric pressure remains roughly constant. This doubling can be thought of as a gradual change occurring over a very long period of time, allowing various physical, chemical, and biological systems to respond slowly to the new conditions, rather than as a sudden shift that might produce rapid or dramatic effects. To understand the implications of such a change, we must first understand several fundamental concepts from physics and chemistry that describe how gases behave, how they interact with other substances, and how living organisms process them. Partial pressure is a concept that describes the contribution of a single gas to the total pressure exerted by a mixture of gases, and it can be understood by imagining that each type of molecule in the air acts independently, colliding with surfaces and with other molecules, as if the other types of molecules were not present, the partial pressure of oxygen, therefore, represents the pressure that would be exerted if only oxygen molecules were present in the same volume and at the same temperature and under normal atmospheric conditions at sea level, where the total atmospheric pressure is approximately 100 kilopascals, or 1 atmosphere. The partial pressure of oxygen is approximately 21 kilopascals, reflecting its 21% concentration. If the concentration of oxygen were to double to 42%, while total pressure remained constant, the partial pressure of oxygen would also double to approximately 42 kilopascals, and this change in partial pressure would have measurable effects on various processes that depend on the availability of oxygen molecules, gas laws, which are mathematical relationships derived from countless observations and experiments, describe how gases respond to changes in pressure, volume, and temperature, and these laws provide a framework for predicting what would happen if atmospheric oxygen levels were to increase. The ideal gas law, expressed as pressure times volume, equals the number of moles times the gas constant times temperature, tells us that for a fixed amount of gas at constant temperature, pressure, and volume are inversely related, and for a fixed volume at constant temperature, pressure is directly proportional to the number of molecules present. Dalton's law of partial pressures states that the total pressure of a gas mixture is the sum of the partial pressures of each component gas, which means that if we increase the number of oxygen molecules while keeping the total number of all molecules constant, we must decrease the number of molecules of other gases, typically nitrogen, to maintain the same total pressure. Modeling the doubling of atmospheric oxygen mathematically requires us to specify how this change occurs over time, whether gradually or suddenly, and to consider the various sources and sinks of oxygen in the Earth system, including photosynthesis by plants and algae, which produces oxygen, and respiration by animals and microorganisms, along with combustion and oxidation reactions, which consume oxygen. In a very simplified model, we might imagine that oxygen production gradually increases while oxygen consumption remains constant, leading to a slow accumulation of oxygen molecules in the atmosphere until a new equilibrium is reached at a higher concentration. Alternatively, we might imagine that oxygen consumption decreases while production remains constant, again leading to accumulation. In reality, both production and consumption rates would likely change in response to the changing oxygen levels, creating a complex feedback system that would require detailed computational modeling to predict accurately the movement of oxygen molecules through air. Occurs primarily through a process called diffusion, which is the random motion of molecules driven by their thermal energy, causing them to spread from regions of higher concentration to regions of lower concentration until the concentration becomes uniform throughout the available space. Each oxygen molecule at room temperature moves at a speed of several hundred meters per second, constantly colliding with other molecules, changing direction with each collision, and traveling only a very short distance between collisions, typically a few tens of nanometers. Despite this rapid motion, the net displacement of any individual molecule over time is much smaller because the motion is random and the molecule is equally likely to move in any direction when oxygen concentration is higher in one location than another, more molecules will randomly move from the high concentration region to the low concentration region, then move in the opposite direction, simply because there are more molecules available to make that journey, and this statistical imbalance produces a net flow of oxygen from high to low concentration areas in an atmosphere with doubled oxygen concentration. Diffusion would still operate according to the same physical principles, but the gradients that drive diffusion might be different in magnitude or location, depending on where oxygen is produced and consumed. For example, in a forest, during daylight hours, oxygen concentration might be slightly higher near the leaves of photosynthesizing plants, creating a gradient that causes oxygen to diffuse away from the leaf surfaces into the surrounding air. And if the overall atmospheric oxygen level were higher, this local gradient would still exist, but would be superimposed on a higher baseline concentration everywhere. Combustion, which is the rapid chemical reaction between oxygen and a fuel substance, releasing energy in the form of heat and light, depends critically on the availability of oxygen molecules and increasing the concentration of oxygen in the air generally makes combustion occur more readily, burn more intensely, and spread more quickly, though these effects follow predictable chemical and physical laws rather than being random or chaotic. When a material burns, oxygen molecules collide with fuel molecules at the surface of the material, and if these collisions have sufficient energy to break chemical bonds and form new bonds between oxygen and fuel atoms, a reaction occurs, releasing energy that heats nearby molecules and increases the rate of further collisions and reactions. The rate of combustion depends on several factors, including the concentration of oxygen, the temperature of the fuel, the surface area available for reaction, and the chemical properties of the fuel itself. In an atmosphere containing 42% oxygen instead of 21%, the rate at which oxygen molecules collide with a fuel surface would approximately double, because there would be twice as many oxygen molecules per unit volume moving at the same average speed, and this would mean that ignition could occur more easily. Fires would burn more intensely, and materials that normally burn slowly might burn more rapidly. However, this does not mean that everything would spontaneously catch fire, because ignition still requires an initial energy input to raise the temperature of the fuel to its ignition point, and many materials have ignition temperatures high enough that they would not ignite at normal environmental temperatures, even with doubled oxygen levels. The relationship between oxygen concentration and combustion rate has been studied extensively in controlled laboratory experiments, where researchers carefully measure how different materials burn under different oxygen concentrations. And these studies show that the effects, while significant, follow predictable patterns that can be described using mathematical equations based on chemical kinetics and thermodynamics. Oxidation rates, which describe how quickly substances react with oxygen, even without visible burning, would also increase in a higher oxygen atmosphere, because oxidation is fundamentally the same type of chemical reaction as combustion, just occurring more slowly and at lower temperatures. Many everyday materials undergo slow oxidation over time, including metals that rust, food that spoils, and organic matter that decays. And all of these processes would proceed more rapidly if oxygen were more abundant. The rate of oxidation typically depends on the concentration of oxygen, according to a power law, where doubling the oxygen concentration might increase the oxidation rate by a factor of 2, or perhaps by a somewhat smaller or larger factor, depending on the specific reaction mechanism and the rate-limiting steps involved when metals are exposed to oxygen in the atmosphere. Oxygen molecules interact with metal atoms at the surface, transferring electrons and forming metal oxide compounds that we commonly recognize as rust on iron or tarnish on silver or patina on copper. The rate at which this occurs depends on the concentration of oxygen in contact with the metal surface, the temperature, the presence of water or other catalysts, and the specific chemical properties of the metal in an atmosphere with doubled oxygen concentration. Metals that currently corrode slowly would corrode more quickly, and protective coatings or treatments that currently last for a certain number of years might degrade in half that time, assuming the corrosion rate scales linearly with oxygen concentration, which is approximately true for many, but not all, corrosion processes. Surfaces of various materials, when exposed to oxygen over time, develop oxide layers that can alter their properties, sometimes protecting the underlying material from further oxidation, as happens with aluminum, which forms a thin, stable oxide layer that prevents deeper corrosion and sometimes allowing continued degradation, as happens with iron, which forms a porous rust layer that does not protect the metal beneath. The thickness and properties of these oxide layers would change in a higher oxygen environment, potentially affecting the long-term durability of structures, machines, and everyday objects in ways that could be predicted through materials science and chemistry, but would require careful experimental study to quantify precisely. Everyday objects made from organic materials, including wood, paper, cloth, and food contain carbon and hydrogen atoms bonded together in complex molecules, and these bonds can be broken through oxidation reactions that gradually decompose the material, releasing carbon dioxide, water, and energy in a higher oxygen atmosphere. These decomposition processes would occur more rapidly, meaning that wood might rot more quickly, paper might yellow and become brittle sooner, cloth might degrade faster, and food might spoil more readily. The magnitude of these effects would depend on the specific material and the conditions under which it is stored, but the general principle is that higher oxygen concentration accelerates oxidative degradation by increasing the rate at which oxygen molecules encounter and react with the material. Oxygen dissolves into water according to Henry's law, which states that the amount of gas dissolved in a liquid at equilibrium is proportional to the partial pressure of that gas in the atmosphere above the liquid, meaning that if the partial pressure of oxygen in the air doubles, the concentration of dissolved oxygen in water at the surface will also double. Once equilibrium is reached, this process of dissolution involves oxygen molecules at the air-water interface occasionally entering the water phase, where they become surrounded by water molecules and move through the liquid by diffusion, while dissolved oxygen molecules occasionally escape back into the air, and at equilibrium, the rate of oxygen entering the water equals the rate of oxygen leaving, resulting in a stable concentration of dissolved oxygen. The concentration of dissolved oxygen in natural water bodies, including oceans, lakes, and rivers, is critically important for aquatic life because fish, invertebrates, and microorganisms all require oxygen for respiration, extracting dissolved oxygen from the water through their gills or cell membranes. Currently, dissolved oxygen concentrations in surface waters are typically in the range of 5 to 10 milligrams per liter, depending on temperature, salinity, and biological activity, and if atmospheric oxygen levels were to double, dissolved oxygen concentrations would also double, potentially reaching 10 to 20 milligrams per liter in surface waters, assuming temperature and other factors remained constant. Oceans exchange oxygen with the atmosphere across the vast air-sea interface, where wind and waves create turbulence that mixes surface water with deeper water and increases the contact area between air and water, facilitating gas exchange. Oxygen that dissolves into surface ocean water is transported to deeper layers by ocean currents, by the sinking of cold, dense water in polar regions, and by biological processes such as the sinking of dead organic matter. And this oxygen supports life throughout the ocean depths. In a higher oxygen atmosphere, the increased dissolved oxygen in surface waters would be transported to depth by the same physical processes, potentially increasing oxygen availability in deep ocean environments, where oxygen is currently limited. Lakes and rivers, being smaller and often shallower than oceans, can experience more rapid changes in dissolved oxygen concentration in response to changes in atmospheric oxygen, because the time required for water to mix and equilibrate with the atmosphere is shorter, and because biological oxygen consumption can vary significantly on short time scales due to changes in temperature, sunlight, and nutrient availability in a doubled oxygen atmosphere. Lakes and rivers would reach higher equilibrium dissolved oxygen concentrations but they might also experience greater fluctuations in dissolved oxygen if biological oxygen consumption rates also increased due to enhanced aerobic metabolism by bacteria and other organisms. Living organisms absorb oxygen through various structures designed to maximize contact between oxygen-containing air or water and the organism's internal fluids, where oxygen is transported to cells that use it in metabolic reactions to extract energy from nutrients in animals that breathe air, including mammals, birds, and many insects. Oxygen enters the body through lungs or tracheal systems, crosses thin membranes into the bloodstream or body fluids, and is carried to cells throughout the body. The efficiency of oxygen absorption depends on the partial pressure of oxygen in the inhaled air, the surface area available for gas exchange, the thickness and permeability of the membranes separating air from blood, and the capacity of blood to carry oxygen. Lungs function by bringing air into close contact with blood, flowing through tiny capillaries, allowing oxygen to diffuse from the air, where its partial pressure is relatively high, into the blood, where its partial pressure is initially lower, until the partial pressures equalize, or until the blood flows away from the lung and is replaced by new blood with low oxygen content. The driving force for this diffusion is the difference in partial pressure, often called the oxygen gradient, and if the partial pressure of oxygen in inhaled air doubles from approximately 21 kilopascals to approximately 42 kilopascals, the gradient driving oxygen into the blood would increase, potentially allowing more oxygen to dissolve into blood plasma and bind to hemoglobin molecules in red blood cells. Hemoglobin, the protein molecule in red blood cells that carries most of the oxygen in blood, can bind up to 4 oxygen molecules per hemoglobin molecule, and the extent to which hemoglobin is saturated with oxygen depends on the partial pressure of oxygen in the surrounding blood plasma, according to a well-characterized relationship called the oxygen-hemoglobin dissociation curve. Under normal atmospheric conditions at sea level, hemoglobin in arterial blood leaving the lungs is typically about 97 to 99% saturated with oxygen, meaning that nearly all available binding sites are occupied. If the partial pressure of oxygen in the lungs were to double, hemoglobin saturation might increase slightly, but because it is already nearly fully saturated under normal conditions, the increase would be small, perhaps reaching 99 to 100% saturation. However, the concentration of oxygen dissolved directly in blood plasma without being bound to hemoglobin would double, and this might have subtle effects on oxygen delivery to tissues, particularly in situations where oxygen demand is very high or blood flow is limited. Blood chemistry responds to changes in oxygen availability through various regulatory mechanisms that adjust breathing rate, heart rate, and blood flow distribution to maintain oxygen delivery to cells within the narrow range required for normal cellular function. If atmospheric oxygen levels were to increase gradually over a long period, these regulatory mechanisms would adjust to the new conditions, potentially altering the baseline breathing rate, the sensitivity of breathing control to carbon dioxide levels, and the production of red blood cells and hemoglobin, though the specific nature and magnitude of these adjustments would depend on the rate of change and would likely vary among different species and individuals. Plants use oxygen in their metabolic processes alongside carbon dioxide because while photosynthesis in chloroplasts uses carbon dioxide and water to produce sugars and releases oxygen, mitochondria in plant cells use oxygen to break down sugars and release energy, just as in animal cells, in a process called aerobic respiration. During the day, when light is available, photosynthesis typically produces more oxygen than the plant's respiration consumes, resulting in net oxygen release to the atmosphere. But at night, when photosynthesis stops, plants consume oxygen through respiration, just as animals do in an atmosphere with doubled oxygen concentration. The rate of plant respiration might increase because oxygen availability would be higher, potentially affecting the balance between carbon fixation through photosynthesis and carbon release through respiration, though the magnitude of this effect would depend on many factors, including light intensity, temperature, water availability, and nutrient availability. Microorganisms, including bacteria, archaea, fungi, and protists, exhibit a wide range of metabolic strategies, some of which require oxygen, some of which are inhibited by oxygen, and some of which can function either with or without oxygen, depending on availability. Aerobic microorganisms, which require oxygen for growth and metabolism, would generally benefit from higher oxygen concentrations, potentially growing faster and metabolizing organic matter more rapidly, while anaerobic microorganisms, which are poisoned by oxygen or cannot use it, might be restricted to environments where oxygen levels remain low, despite the higher atmospheric concentration, such as waterlogged soils, deep sediments, or the intestines of animals. The overall balance of microbial communities in various environments might shift in response to long-term changes in oxygen concentration, favoring aerobic species in environments where oxygen penetration increases and potentially affecting nutrient cycling, decomposition rates, and the production of various gases, such as methane, carbon dioxide, and nitrogen compounds. Atmospheric circulation, driven by the uneven heating of Earth's surface by the sun, moves air masses horizontally and vertically, mixing gases and distributing heat, moisture, and momentum across the planet. The basic patterns of atmospheric circulation, including the Hadley cells in tropical regions, the Ferrel cells in mid-latitudes, and the polar cells in high latitudes, along with the jet streams and prevailing winds, would continue to operate in the same general manner, even if oxygen concentration were to double, because these patterns are determined primarily by the distribution of solar heating, the rotation of the Earth, and the properties of air as a fluid, which would not change dramatically due to a change in composition from 78% nitrogen and 21% oxygen to a mixture containing 42% oxygen and reduced nitrogen. However, subtle changes in air density, heat capacity, and other thermodynamic properties might slightly alter the strength or position of circulation features, though such changes would likely be small compared to the variations caused by other factors, such as seasonal changes, ocean currents, and topography, temperature, and pressure influence oxygen behavior in accordance with the general gas laws, where increasing temperature causes gas molecules to move faster and exert greater pressure if confined to a fixed volume, while increasing pressure forces molecules closer together. If temperature is held constant, oxygen molecules at higher temperatures have greater kinetic energy and collide more frequently with surfaces and with other molecules, which can increase the rate of chemical reactions such as oxidation and combustion, while oxygen at higher pressures has greater density and greater partial pressure, which also tends to increase reaction rates and the amount of oxygen dissolved in liquids. In Earth's atmosphere, temperature decreases with altitude. In the troposphere, the lowest layer of the atmosphere, where weather occurs, which means that oxygen molecules move more slowly and exert less pressure at high altitudes, while pressure decreases with altitude because there is less weight of air above, which reduces the density and partial pressure of oxygen. If the concentration of oxygen were to double uniformly throughout the atmosphere, these same altitude variations would persist, but the partial pressure of oxygen at any given altitude would be twice what it currently is. Measurement instruments used to detect changes in oxygen levels include electrochemical sensors, which measure oxygen concentration by monitoring the current produced when oxygen molecules are reduced at an electrode surface. Optical sensors, which measure oxygen concentration by detecting changes in fluorescence or absorption of light caused by the presence of oxygen, and paramagnetic analyzers, which exploit the fact that oxygen molecules are attracted to magnetic fields due to their unpaired electrons, allowing oxygen concentration to be determined by measuring the force exerted on a sample in a magnetic field. These instruments can be calibrated to provide accurate measurements of oxygen concentration over a range of conditions, and they are used in applications ranging from monitoring industrial processes to measuring dissolved oxygen in water to analyzing atmospheric composition in scientific research, repeated measurements using well-calibrated instruments under controlled conditions allow researchers to detect small changes in oxygen concentration and to verify that the instruments are functioning correctly by comparing results from different instruments or different measurement techniques. Repeated experiments designed to study how oxygen concentration affects various physical, chemical, and biological processes confirm that the behaviors observed are predictable and reproducible, meaning that under the same conditions of temperature, pressure, and oxygen concentration, the same outcomes are obtained within the limits of experimental uncertainty. This reproducibility is a fundamental principle of science, allowing researchers to build confidence in their understanding of how systems work and to develop mathematical models that can predict behavior under conditions that have not yet been tested experimentally. For example, experiments that measure how quickly different materials oxidize at various oxygen concentrations can be used to develop equations that describe oxidation rate as a function of oxygen concentration, temperature, and other variables, and these equations can then be used to predict oxidation rates at higher oxygen concentrations that may not have been tested directly. Mathematical models used to estimate long-term equilibrium in the atmosphere when oxygen levels change must account for the many processes that produce and consume oxygen, including photosynthesis, respiration, combustion, weathering of rocks, volcanic emissions, and burial of organic carbon in sediments, along with the transport of oxygen by atmospheric circulation and ocean currents. These models typically involve systems of differential equations that describe how the concentrations of various gases change over time in response to sources, sinks, and transport processes, and solving these equations requires numerical methods implemented on computers because the equations are too complex to solve analytically. The models can be used to explore hypothetical scenarios, such as what would happen if photosynthesis rates increased or if combustion rates decreased, and to estimate how long it would take for the atmosphere to reach a new equilibrium state with different oxygen concentration, probability, and statistics. Describe the molecular motion of oxygen in terms of distributions and averages, recognizing that individual molecules move randomly and unpredictably, but that large collections of molecules exhibit regular and predictable behavior. The Maxwell-Boltzmann distribution describes the range of speeds that molecules in a gas possess at a given temperature, showing that while most molecules move at speeds near the average, some move much faster and some move much slower, and this distribution can be used to calculate average quantities such as the mean speed, the root mean square speed, and the most probable speed. Statistical mechanics, the branch of physics that connects the microscopic behavior of individual molecules to the macroscopic properties of gases, provides the theoretical foundation for understanding how pressure, temperature, and other observable properties emerge from the collective behavior of vast numbers of randomly moving molecules. Time and gradual change, shape, chemical, and biological responses to environmental perturbations, because many systems have inertia or memory that prevents them from responding instantaneously to new conditions, and because adaptation and adjustment often require processes that operate over long timescales, such as the growth of new tissues, the evolution of new traits through natural selection, or the accumulation of chemical products through slow reactions. If atmospheric oxygen concentration were to increase gradually over thousands or millions of years, organisms and ecosystems would have time to adapt through evolutionary processes, potentially developing new physiological mechanisms to cope with higher oxygen levels, or to exploit the opportunities created by greater oxygen availability. Chemical systems, such as the oxidation of minerals in soils, or the weathering of rocks, would reach new steady states as reaction rates increased and as the concentrations of reactants and products adjusted to balance the higher oxygen input. Scientific uncertainty reflects the limits of measurement tools, the variability inherent in natural systems, and the gaps in our understanding of complex processes, and it is quantified using statistical methods that estimate the range of possible values consistent with observations and theory. When scientists report a measurement or a model prediction, they typically include an uncertainty estimate, often expressed as a standard deviation or a confidence interval, indicating how much the true value might differ from the reported value due to measurement errors, natural variability, or model limitations. Acknowledging uncertainty is an essential part of scientific practice because it communicates the reliability of knowledge and identifies where further research is needed to improve understanding. Scientific definitions remain stable over time as models improve, because definitions are carefully chosen to be based on fundamental concepts, or on reproducible measurement procedures that do not depend on specific theories or assumptions that might change. For example, the definition of oxygen concentration as the number of oxygen molecules per unit volume, or as the partial pressure of oxygen, remains valid regardless of what theories we develop to explain how oxygen behaves, or what models we build to predict atmospheric composition as measurement techniques improve, becoming more precise and more accurate. The numerical values assigned to quantities may be refined, but the definitions themselves remain consistent, allowing scientific knowledge to accumulate in a coherent manner, rather than needing to be rewritten each time a new discovery is made. Physical and chemical laws governing gases, including the ideal gas law, Dalton's law of partial pressures, Henry's law of gas solubility, and the laws of thermodynamics remain consistent across a wide range of conditions and are not expected to change if atmospheric composition changes, because these laws describe fundamental relationships that have been tested extensively and found to hold under many different circumstances. These laws are approximate rather than exact, and they work best under certain conditions, such as low pressure and high temperature, where gases behave ideally, but they provide useful and accurate descriptions of gas behavior for most purposes, including understanding what would happen if oxygen concentration in the atmosphere were to double. Structured scientific reasoning stays balanced between observation and mathematics by using observations to test mathematical models, and by using mathematical models to guide new observations, creating a cycle of prediction, measurement, and refinement that progressively improves our understanding of natural phenomena. When studying atmospheric oxygen, scientists make observations of current oxygen levels, of how oxygen is produced and consumed, and of how oxygen affects various processes, and they use these observations to develop mathematical models that describe oxygen cycling and predict how oxygen levels might change in the future or might have been different in the past. The models make specific predictions that can be tested through new observations, and if the predictions match the observations, confidence in the model increases, while if the predictions do not match, the model must be revised to account for the discrepancy. This iterative process, repeated many times by many scientists, leads to increasingly accurate and comprehensive understanding. Scientific language becomes more precise over repeated study as researchers identify ambiguities, refine terminology, and develop standardized ways of describing phenomena that allow clear communication across different research groups, different disciplines, and different time periods. Technical terms in science are often defined very specifically to avoid confusion, and units of measurement are standardized internationally to ensure that measurements made in different places can be compared directly. When discussing atmospheric oxygen, scientists use specific terms such as mole fraction, partial pressure, and concentration, each with a precise definition, and they report measurements in standard units such as kilopascals for pressure, moles per cubic meter for concentration, or percent by volume for composition, allowing quantitative comparisons and calculations to be performed reliably. The movement of molecules continues without ceasing, driven by thermal energy. that cannot be removed entirely unless the temperature reaches absolute zero, which is unattainable in practice. And this perpetual motion ensures that gases remain mixed, that diffusion proceeds to eliminate concentration gradients, and that chemical reactions continue to occur whenever the necessary conditions are met in an atmosphere with doubled oxygen concentration. This fundamental molecular activity would continue unchanged in its basic character, with oxygen molecules moving, colliding, reacting, and dissolving according to the same physical principles that govern their behavior now, but with the quantitative outcomes shifted to reflect the higher concentration of oxygen molecules available to participate in these processes. The explanation of these processes requires careful attention to detail and to the logical connections between different concepts, building from simple observations about gases and molecules to more complex descriptions of chemical reactions, biological systems, and atmospheric dynamics. Each step in the explanation can be verified through experiment or observation, and the overall picture that emerges is one of a system governed by physical and chemical laws that operate consistently and predictably, even when conditions change. The doubling of atmospheric oxygen represents a significant change in environmental conditions, but it does not represent a breakdown or suspension of the laws of nature, and the consequences of such a change can be understood and predicted using the tools and methods of science. As we consider the many ways that oxygen interacts with the environment, from the slow oxidation of materials to the rapid energy release in combustion, from the dissolution of oxygen in water to the uptake of oxygen by living cells, from the transport of oxygen by winds and currents to the cycling of oxygen through photosynthesis and respiration, we see that oxygen is intimately connected to virtually every aspect of Earth's physical, chemical, and biological systems. Understanding how these systems would respond to a change in oxygen concentration requires knowledge from many scientific disciplines, including physics, to describe molecular motion and gas behavior, chemistry, to describe oxidation and other reactions, biology, to describe how organisms use oxygen and how they might adapt to different oxygen levels, atmospheric science, to describe how oxygen is distributed and transported, and mathematics, to describe rates, equilibria, and dynamics. Quantitatively, the questions we might ask about a doubled oxygen atmosphere are numerous and varied, including questions about combustion risk, about material degradation, about health effects on humans and other animals, about changes in aquatic ecosystems, about agricultural impacts, about atmospheric chemistry and climate, and about long-term evolutionary consequences. Each of these questions can be addressed using scientific methods, gathering relevant data, developing hypotheses, testing predictions, and refining understanding based on evidence. The process is gradual and methodical, building knowledge piece by piece, and the answers that emerge are provisional, always subject to revision as new evidence becomes available or as new theoretical insights are developed. The relationship between oxygen concentration and reaction rates is not always simple or linear, because many reactions involve multiple steps, some of which may be more sensitive to oxygen concentration than others, and because reaction rates can be affected by factors other than oxygen availability, including temperature, the presence of catalysts or inhibitors, and the physical state and accessibility of reactants. Detailed studies of specific reactions under controlled conditions, are necessary to understand these complexities and to develop accurate predictive models. Similarly, the responses of biological organisms to changes in oxygen concentration are complex and multifaceted, involving physiological adjustments to maintain cellular oxygen supply, behavioral changes to avoid hypoxia or hyperoxia, and potentially evolutionary adaptations that alter anatomy, physiology, or biochemistry over many generations. The study of how organisms respond to environmental change is an active area of research in biology, drawing on techniques from ecology, physiology, genetics, and evolutionary biology to understand both short-term and long-term responses. The atmosphere itself is a dynamic system, constantly changing on multiple timescales, from the rapid fluctuations associated with weather to the slower variations associated with seasons and climate, to the very slow changes associated with geological processes and biological evolution. Understanding how the atmosphere might change in response to altered oxygen levels requires considering all of these timescales and the processes operating on each, from the instantaneous mixing of gases by turbulence to the gradual accumulation or depletion of gases through photosynthesis, respiration, weathering, and volcanic activity. The study of Earth's atmosphere is informed by observations of the present atmosphere, by studies of past atmospheres preserved in ice cores, sediments, and rocks, and by comparisons with the atmospheres of other planets, which provide natural experiments showing how atmospheric composition and dynamics can differ under different conditions. These diverse sources of information help scientists build a comprehensive understanding of how atmospheres work and how they change. In considering what would happen if oxygen levels doubled, we are engaging In a thought experiment, a hypothetical scenario that allows us to explore the implications of our scientific understanding by applying known principles to new situations. Such thought experiments are valuable in science because they help clarify our thinking, identify gaps in our knowledge, and generate predictions that can guide future research. While we may never experience a doubling of atmospheric oxygen, in reality, thinking through the consequences of such a change helps us understand better how oxygen functions in the Earth system and how sensitive various processes are to changes in oxygen availability. The continuous nature of physical and chemical processes means that small changes in conditions generally produce small changes in outcomes, allowing us to predict the direction and approximate magnitude of effects, even when we cannot calculate exact numbers. This continuity reflects the underlying smoothness of the mathematical functions that describe natural laws, and it provides a basis for confidence in our predictions, because dramatic discontinuities or threshold effects are relatively rare in well-understood physical and chemical systems. The accumulation of scientific knowledge about oxygen and its role in Earth systems represents the work of many generations of researchers, each building on the findings of those who came before, gradually refining measurements, improving theories, and expanding the scope of investigation. This cumulative process is characteristic of science, and it produces a body of knowledge that is both reliable and progressive, with newer findings generally confirming and extending earlier findings rather than overturning them completely. As oxygen molecules continue their ceaseless motion through the atmosphere, dissolving into water, entering living cells, reacting with surfaces, and participating in countless chemical transformations. The systems they are part of continue to function according to physical and chemical principles that have operated throughout Earth's history and will continue to operate into the future. The scientific study of these systems provides insight into how the world works, how it has changed, and how it might change in response to different conditions, all expressed in the careful, measured language of observation, measurement, calculation, and logical reasoning that characterizes the scientific approach to understanding nature. The gradual accumulation of oxygen molecules in the atmosphere. If such a process were to occur over geological timescales spanning millions of years, would represent a shift in the balance between oxygen-producing and oxygen-consuming processes that currently maintain atmospheric oxygen at approximately 21% of atmospheric composition. Scientists who study the history of Earth's atmosphere have found evidence that oxygen levels have varied considerably over the planet's 4.5 billion year history, from essentially zero oxygen in the early atmosphere before the evolution of photosynthetic organisms to periods during which oxygen may have been somewhat higher or lower than current levels, and these historical variations provide a context for understanding how atmospheric composition can change and what factors control the rate and direction of change. The study of ancient atmospheres relies on indirect evidence preserved in rocks, including the oxidation state of iron in sedimentary rocks, the isotopic composition of carbon and sulfur compounds, and the presence or absence of minerals that can only form under specific oxygen concentrations. By analyzing these geological records carefully, researchers can reconstruct approximate oxygen levels at different times in Earth's past, though with considerable uncertainty due to the complexity of interpreting ancient chemical signatures, the mechanisms that regulate atmospheric oxygen concentration, operate through feedback loops involving photosynthesis, which produces oxygen, and various oxygen-consuming processes, including aerobic respiration by organisms, combustion of organic matter in fires, and the weathering of rocks containing reduced minerals, such as iron sulfides. When oxygen levels rise, the rate of oxygen-consuming processes tends to increase because higher oxygen concentration accelerates oxidation reactions, and this increased consumption tends to slow or reverse the rise in oxygen, creating a negative feedback that stabilizes oxygen concentration around some equilibrium value. Conversely, when oxygen levels fall, oxygen-consuming processes slow down, allowing oxygen production to exceed consumption and drive levels back upward. These feedback mechanisms do not operate instantaneously, but rather over timescales ranging from years to millions of years, depending on which processes are most important in a given situation, and the strength of the feedbacks determines how quickly the system responds to perturbations and how stable the equilibrium is. In a hypothetical scenario where oxygen levels gradually doubled from 21 to 42%, the increased rate of oxidation would affect the cycling of many chemical elements through the environment, including carbon, nitrogen, sulfur, and iron, each of which can exist in multiple oxidation states, and each of which plays important roles in biological and geological processes. Carbon in organic matter would oxidize more readily to carbon dioxide, potentially affecting the amount of carbon stored in soils, sediments, and living biomass. Nitrogen compounds might be oxidized to different nitrogen oxides more readily, affecting soil nitrogen availability and atmospheric chemistry. Sulfur compounds in minerals would weather more quickly, releasing sulfate to rivers and oceans. Iron in rocks and soils would oxidize from ferrous to ferric forms, changing the color and chemical properties of geological materials. The ocean's role in the global oxygen cycle would also be affected by changes in atmospheric oxygen concentration, because the ocean contains dissolved oxygen that supports marine life, and the amount of dissolved oxygen depends on the equilibrium between oxygen dissolving from the atmosphere and oxygen being consumed by respiration and decomposition of organic matter in seawater. If atmospheric oxygen partial pressure doubled, the equilibrium concentration of dissolved oxygen in surface seawater would also double, assuming temperature and salinity remained constant, but the actual concentration at any given time and place would depend on local biological activity, water circulation patterns, and the history of the water mass. Deep ocean waters, which are isolated from the atmosphere for hundreds to thousands of years, as they circulate through the global ocean conveyor system, would only gradually equilibrate with a higher atmospheric oxygen level. And during the transition period, there might be a gradient of dissolved oxygen concentrations, with surface waters having higher concentrations that reflect the new atmospheric level, and deep waters retaining lower concentrations that reflect conditions when the water was last at the surface. The biological pump, which transports carbon and other elements from the surface ocean to the deep ocean through the sinking of dead organisms and fecal material, also transports oxygen in the form of dissolved oxygen that is consumed as organic matter decomposes. At depth, changes in oxygen availability could affect the depth to which organic matter is decomposed before reaching the seafloor, potentially altering the burial of organic carbon in marine sediments, which over geological timescales affects atmospheric carbon dioxide levels and climate. These interconnections between oxygen, carbon, and climate illustrate the complexity of Earth system science, where changes in one component can propagate through the system, affecting many other components. in ways that may reinforce or counteract the original change. Temperature effects on oxygen behavior extend beyond the basic gas law relationships to include effects on biological metabolism, chemical reaction rates, and physical properties of materials. Higher temperatures increase the kinetic energy of molecules, causing them to move faster and react more readily, which means that at higher temperatures, oxidation and combustion would be further accelerated beyond the acceleration caused by increased oxygen concentration alone, creating a multiplicative effect. Conversely, at lower temperatures, reaction rates slow down, and the effects of increased oxygen concentration would be partially offset by the reduced reactivity associated with lower molecular speeds. Living organisms are sensitive to temperature because biochemical reactions in cells are catalyzed by enzymes, which are protein molecules whose shape and function depend on temperature. Each organism has a range of temperatures within which it can function normally, with performance typically peaking at some optimal temperature and declining at higher or lower temperatures. Changes in oxygen availability could shift the optimal temperature for some organisms, or could alter their tolerance to temperature extremes, though predicting such effects requires detailed knowledge of the organism's physiology and the specific biochemical pathways affected by oxygen concentration. The timescale of change is critically important in determining how systems respond, because slow changes allow time for adjustment and adaptation, while rapid changes may exceed the capacity of organisms or ecosystems to respond, potentially leading to disruption or collapse. If oxygen levels were to double over millions of years, organisms would experience many generations during which natural selection could favor individuals with traits that performed well under the gradually changing conditions, leading to evolutionary adaptation that might minimize the negative impacts of change, or even allow organisms to benefit from new opportunities created by higher oxygen availability. In contrast, if oxygen levels were to double over years or decades, many organisms would not have time to adapt genetically, and the responses would be primarily physiological and behavioral, with potential for significant stress, reduced fitness, or mortality if the changes exceeded tolerance limits. The distribution of oxygen throughout the atmosphere varies slightly with altitude, latitude, and time, reflecting the balance between mixing processes that tend to homogenize composition and sources and sinks that create spatial variations. In the troposphere, the lowest layer of the atmosphere, where most weather occurs and where organisms live, oxygen is relatively well mixed by turbulent winds and convection, and composition varies by less than 1% from place to place under normal conditions. In the stratosphere, the layer above the troposphere, where temperature increases with altitude due to absorption of ultraviolet radiation by ozone, oxygen molecules can be broken apart by ultraviolet light to form individual oxygen atoms, which can then recombine with oxygen molecules to form ozone, a molecule consisting of 3 oxygen atoms. This photochemical cycling creates a vertical profile of oxygen and ozone concentrations that is important for protecting life on Earth's surface from harmful ultraviolet radiation. If atmospheric oxygen concentration at the surface were to double, the stratospheric oxygen and ozone chemistry would also change, potentially affecting the ozone layer and the amount of ultraviolet radiation reaching the surface, though the details would depend on complex photochemical modeling that accounts for the rates of many different reactions occurring simultaneously at different altitudes. The scientific instruments used to measure atmospheric composition have evolved considerably over the history of atmospheric science, from early chemical methods that involved collecting air samples and analyzing them in laboratories, using wet chemistry techniques, to modern automated sensors that continuously monitor composition and transmit data electronically. The accuracy and precision of measurements have improved dramatically, allowing scientists to detect changes of less than 1 part per million in the concentration of trace gases, and to track these changes over time with confidence. Long-term monitoring stations distributed around the world continuously measure atmospheric composition, providing data that documents how composition is changing due to human activities and natural processes. This monitoring network would be essential for detecting any gradual change in oxygen concentration, should such a change occur, allowing scientists to track the rate of change and to study the factors responsible. And now, as the air settles into its quiet balance, as oceans, rivers, and skies continue without urgency, there is nowhere anything needs to change, nothing more to unfold, nothing to resist. The atmosphere, in its composition, is not idle. It simply circulates, diffuses, reacts. Processes slowing. Energy conserved. Molecules moving quietly. Without attention. Let the increase in oxygen remain neutral. Neither good nor bad. Just present. Just ordinary. Let the unseen continue its silent work. Oxygen dissolving. Organisms breathing. Materials oxidizing. All according to the same rules. Without interference. Without observation. Your body follows the same rules. Slowing. Reducing effort. Releasing activity. Thoughts may thin out. Not disappearing. Just becoming less active. Less demanding. Breath continues on its own. Steady. Unforced. Unremarkable. As oceans, forests, and soil adjust to this subtle change, you may also remain still, doing nothing, needing nothing. Sleep is simply a phase, like molecular motion, like gas diffusion, like slow chemical reactions, like rest in living systems. There is no message, no meaning to uncover, only continuation. And as Earth's systems continue in silent stability, you may drift without effort into sleep, not as an ending, not as a beginning, just a pause within an ongoing system. Good night and rest within the quiet of the natural world.